The Diels-Alder reaction. It's a reaction that helps you make a six-membered ring. It's a very important reaction. Now let's begin. The Diels-Alder reaction involves a diene and a dienophile. So this is the diene, and this right here is the dienophile. So you can see your conjugated diene right here. The reaction is going to take place the following way. The diene and the dienophile are going to react in a concerted manner, meaning the reaction is going to take place in one step, and it's going to happen the following way. The dienophile is going to attack the carbon at the end of the diene. Double bond is going to shift in between, and then finally the double bond in the diene is going to attack the dienophile. Now, before I show you the product here, you should be aware that you have 2 pi electrons in this one because you have a double bond, and here you have 4 pi electrons because you have 2 double bonds. So that's why it's called a 4+2 cycloaddition. The dienophile is called the dienophile. Basically, it's the lover of the diene. Comes from philia, which is to love. So here is the product, and this is what I need you to pay attention to. I'm going to do the following. I'm going to highlight the diene in yellow, and then highlight the dienophile in green. So look what happened. You formed a 6-membered ring, and let me do the highlighting here. This is your yellow, and you should know that a double bond shifted in between right here. Where's your dienophile? It's right here. You can also number that. You can number it in any way you want. You can say this is 1, 2, 3, 4, 5, and 6. And here it is 1, 2, 3, 4, 5, and 6. Okay, here's another reaction. Now this is with an alkyne, same process. These electrons shift in between, and of course, these attack at the end. And now you should be aware that now you have your double bond here. So let's use the highlighting one more time. And then you should know that we still have a double bond here because one of them was used to form a bond, but there's still one that remains right there. So here's the product for the first one, and here's the product for the second one. It takes a little bit to see it at first, but it makes sense as, again, you look at it multiple times. So again, that's why it's called a 4+2 cycloaddition, because the ring is formed between the interaction of the 4 pi electrons in the dienes and the 2 pi electrons in the alkene or the alkyne or the dienophile. Very well. So let's actually apply this to other examples. Again, the movement is the same way. So this tacks this way, that way. I'm going to show you also another method that is often used. I'm going to apply it on the next reaction or in other reactions. So again, the same thing applies here. Here's our double bond. And of course, we have our CN, or our nitrile group. So for this one here, you're going to need to visualize this, or you just need a little bit of visualization and you'll get it. So with this here, you have a ring and we have an alkyne. So I'm going to draw dots where the connection is going to take place. And again, it's going to go this way. These are going to shift in between, and then these are going to add that way. Imagine this is a potential bond. So it's going to need electrons, and those electrons are coming in from the double bond and forming a bond right there. And then the same thing is happening with the bond on the top. Now, how do you form this? This looks a bit interesting here. You would form the following. So to draw this, you can do it the following way. And again, I'm not trying to be perfect here. It's not easy to draw this, especially. Okay, here it is, not bad. So you might be looking and saying, okay, what is happening here? Where did this come from? So imagine this. Cyclopentadiene ring. Imagine this right here is the flap. I'm going to actually show you that. Just bear with me. I'm going to explain in a second, and I'll show you another way of drawing this. Okay. So I'm going to use to highlight this. So the highlighting here is, watch how it looks like. It's all of this right there. So the flap that's going all the way, or what we call, or at the top, that's your cyclopentadiene ring, pentadiene ring. And then of course, what's left is your, I don't want to use a different highlighter. What's left is what came from the alkyne right here. So that should make a little bit of sense. I'll explain when we meet in lecture. There's a name for this. This is called a abridged bicyclic structure. There's another way of drawing this, is you could also form the cyclohexane ring. Here are your two bonds, two double bonds. Attach the substituents. And then this flap or this bridge head position, the top, I'm going to use a different color. You can show this this way. Look at it in both ways. It takes a looking at it from a different perspective. Imagine you're looking at it from the side here, but imagine you're looking at this from the top. The important thing to remember to finish this page with is that this is a concerted reaction. Reactant bonds are broken and product bonds are formed at the same time. And the mechanism does not involve radical or ionic intermediate. There is no carbocation, carbanion, or a radical intermediate. So all happens at the same time.